Welcome to Module 6 on genomic selection, and in this module we're going to talk about some of the basic principles of genomic selections as they apply to a breeding program and implementing genomic selection, and in particular we'll talk about the training population. Just to rehash a little bit, here is your basic steps in genomic selection. You got your training population, it's phenotyped, genotyped, you build the model, you cross the best individuals, get progeny from the cross, genotype the progeny and predict their values. And then from there you can just start going through the cycles of genomic selection by repeating these steps down here. Steps 1 and 2 are absolutely crucial. We will not talk about proper phenotyping. Most people already are familiar with that, and we'll talk about that in a different class. But let's talk now about the training population itself. And I guess first we'll talk about many factors that impact the effectiveness of genomic selection. First of all, of course, is the training population. But other things is the architecture of the trait. How many genes are there? Are they small effect genes, large effect genes? You know, if your trait is controlled by simply 1 or 2 genes with very large effects, you don't want to do genomic selection. You want to do marker-assisted selection. There's also effectiveness of genomic selection, determined by the number of markers you have scattered throughout the genome. It can be affected some by what model you use in your genomic selection, whether you revise the model, and the phenotyping. I've highlighted the top one and the bottom one because these are absolutely crucial, and these are things that you truly do control as a breeder. Let's talk about the training population. It's very important to have a good size of your training population. You'd like to see the affected population size. I won't go into that. You want to consider the relationship of your training population to the individuals you're going to actually do genomic selection in, where you're going to predict their value based solely on genotypes, and the structure of the population, and of course errors, outliers, and really the heritability of your phenotypes. The training population. First of all, it should be fairly large, maybe over 300 lines, and that depends on your trait and the structure of the population, how related the individuals are. We'll talk about some of that in a little bit. Your training population really should be relevant to variety development. Again, I look at genomic selection as a breeding tool, not so much a genetics tool or a basic research tool, but as something that is for variety development. So you need to have a training population that is relevant to developing new varieties. The training population must be related to the individuals you hope to actually implement genomic selection in and select on based solely on genotype. The training population must have phenotypic and genetic variation. You can't have a training population where all the individuals are resistant and try to build a model, because it just simply will not work. You have to have variation. Your training population ideally would have a very limited population structure, and you must be able to phenotype the training population in relevant environments and with enough observations to produce high heritability. What are some of the sources of training populations? Well, we'll go through these. A primary source is the lines you already have in your breeding population now. You already have them, they're already established, you're already phenotyping, you're familiar with them, they're probably very relevant to developing new varieties. That can be an ideal training population. You can look at lines and data that come out of cooperative tests, either past tests or planned tests for the future. And these may be lines from multiple programs that are being tested cooperatively by all the breeders in those programs. You can do genomic selection even in biparental populations. So now some populations I feel are probably less appropriate for genomic selection would be things like germplasm collections, because germplasm collections may not have high yield. They may not be good for most of the traits you need to improve that you want to consider when you're developing new varieties. Germplasm collections can be highly structured, and that can cause problems. As I said, they're not really well suited for variety development. I think of genomic selection as a variety development tool, and they actually can be very difficult to phenotype if many of the individuals in the germplasm collection are poorly adapted. So that presents a lot of problems. So I would try to avoid germplasm collections for doing genomic selection. They're good for maybe finding genes and doing association analysis, but really not well suited for genomic selection. Some considerations when you're looking at training populations. And again, you could look at, I'm suggesting 3 sources here: your breeding program, cooperative tests, biparental populations. And I'd like you to strongly consider just the material you already have in your breeding programs. It's already been created. It's very relevant to your objectives of variety development. The lines in that populations can be quite related, which gives you some nice power in your genomic selection. You're already going to phenotype them, so you already have invested in the phenotypes. It doesn't require any additional resources to phenotype them. You're already spending the money to do that. There's probably not too much structure within that population. You will have to question will there be adequate variation for your traits. Let's say you are looking for disease resistance and all your lines in your breeding population are susceptible. Well, then that's not really a good population for genomic selection for that trait. In some cases, your phenotyping may not be very extensive. You're looking only within your program. You may have only a few environments of data for a large set of lines. Cooperative tests can also be very relevant if they're elite breeding material from other programs. You usually have to allocate extra phenotyping resources to these type of trials, but it can be worth it. The structure in these may be minimal, especially if you get lines from related programs. And there could be issues, though, if some of the lines are really not very related to your program or to each other. In other words, there's some lines that simply are not very related and therefore really cannot be very useful in predictions. Historical data on these tests might be available, though you do have to standardize it, and we'll talk about that later. Cooperative tests are often extensively phenotyped over many different environments, and that's a nice thing. But all those environments where they're tested may not be relevant to your objectives. So you may want to comb through that data and pick out the phenotypic data from the locations that are most relevant to you. Biparental populations can be used. Nice thing about them, there's absolutely no structure within a biparental population, and all the individuals are very related, so the accuracy can be high. The size can actually be smaller because all lines in there are full sibs. The more related lines are, the smaller your training population has to be. And in no population are lines more related to one another than they are within a biparental cross. Lines, these biparental populations are probably going to require additional phenotyping beyond what you normally do in your variety development program. And you have to wonder if the model you built within a single biparental population will have relevance beyond that cross itself. Here's some examples of training populations, and I'm simply displaying, let's say, a collection of lines that are being that have all been genotyped, and we're looking at graphs of principal component analysis. And so we're kind of looking at the genetic space within a population. And here's a nice training population. The lines are all within one region of the genetic space. They're fairly related to one another. And there's limited population structure here, and that's a good training population. Here'd be an example of one that's not so good. Here you have a large group of lines that are related to one another. That's good. But then you got a little group out here that's an outlier, and 2 other groups up here that are outliers. And this type of structure is really not the kind of population that you'd like to do genomic selection in. In fact, I could argue also it's not that great for doing association analyses in either. So you want to try to avoid these highly structured populations for your training populations. And again, when you look at lines within your breeding program, oftentimes they'll look more like this population structure than the one on the right. With that, we're going to pick up this subject, continue it in the second half of Module 6.